Hello and welcome back to High Peak Education. In this video, I would like to perform a lecture on magnetic fields and their relationship to electric currents. We know from earlier lectures and earlier videos that I've posted that magnetism arises from moving charges. We know that electric currents are moving charges. But so far, we've only looked at movement of charge insofar as at the atomic level and nearly permanent magnets and charged particles moving through magnetic fields. But now let us consider how magnetic fields are generated by electric current. So let's start off with the simplest example we could think of. That is the magnetic force on a current carrying wire. So we know that if moving charges produce a magnetic field, and we also know if a charge moving through a magnetic field experiences a magnetic force, then charge moving in a wire should experience a magnetic force as well. So if an external magnetic field exerts a force on moving charges, then the force will be exerted on a conductor carrying current. Since charges are bound to flow in the path of the wire itself will experience a force. And from magnetic force equation for a moving charge, we can derive the vector force for a straight wire of length L. So the derivation is actually very similar to what we've seen before for magnetic force. Instead of QV cross B, what if Q actually changes in time? Well, that's electric current. But what if the distance does not change in time? Well, that's going to be basically the length of the wire. So we would get, if there's a length vector, that is some vector length pointing in the direction of current I, we would have the following vector equation. That the magnetic force vector is equal to the electric current multiplied by the length vector cross product with the magnetic field. That is to say, L cross B times I, and I being a current, should give F sub B. So in units, that's amperes times meters times Teslas should give newtons. L vector is the magnitude of the length segment. And by the way, this equation for now only applies to a straight segment of wire in a uniform external magnetic field. Very soon we will relax that constraint and allow this segment of wire to not necessarily be straight, and perhaps even the magnetic field to be slightly different. So here are the resulting effects of magnetic forces on current carrying wires. So the first thing is the direction of the force is given by the right-hand rule that we saw before, but I will call this right-hand rule number 1B, sort of the companion to right-hand rule 1, where I is now a lot of moving charges. Okay, so let's imagine this example. So previously we did QV cross B, where it was a single charge moving at a certain velocity. Well, current, that is electric current, is just a chain of moving charges, all in the same direction. In fact, in the direction of the so-called length vector. So, imagine in this diagram, the current is moving upward. So we would point our fingers in the direction of the moving electric current. The magnetic field is into the page, so the thumb points to the left. And since it points to the left, that should be a leftward force. That is a leftward magnetic force. Now, what if the current is running down in the diagram? Point your fingers down, magnetic field into the page. The thumb points in the rightward direction. If you want to use the three fingers, remember the pointing finger has to be the current. The right thumb has to be the magnetic field, and then the actual magnetic force is the third finger. Okay, so you can do that way too. That'll work. Okay. So that's kind of the idea. So just like shown here, if you point your thumb in the direction of the current, the pointing finger is the direction of the magnetic field, and then the direction of the third finger is the direction of the magnetic force. So however you resolve that, hopefully make sure you get the right answer. So notice again, the magnetic force is always going to be perpendicular to the plane formed by the current times the length vector direction and the magnetic field vector. So even if the length vector and the magnetic field vector are not 90 degrees to one another, the magnetic force will always be perpendicular to that plane. So the ways to reverse the direction of the force include to reverse the current direction or to reverse the direction of the magnetic field, but not both. If you reverse both, the magnetic force would be in the same direction. Remember that the X and the dot mean into the page and out of the page. So if an electric current goes into the page, we'll also use the same convention, an X with a circle around it, and if the electric current is coming out of the page, that'll be a circle around it with a dot. So let's proceed and look at a couple more examples. Okay? So that last one was the effects of magnetic forces on current carrying wires. What about some pictorial depictions of these magnetic force on current carrying wires? So it turns out this causes wires to be deflected. So IL cross B is the direction of the magnetic force. So if the wire carries current, the magnetic field will exert a force on moving charges, causing the wire to deflect. Now, what if we have a slightly different situation? What if we don't have a straight current carrying wire? What if we have a loop? Well, this loop, imagine that it's cut by this plane. And notice that this green plane is kind of a three-dimensional representation. Notice at the bottom of the loop, the current is going into the page. At the top of the loop, the current is coming out of the page. So notice, when the current goes into the page, we see an X. When the current comes out of the page, we see a dot. And notice that this is sort of a side view of the loop. And then this is basically a view, an edge view of the loop, where you see half the loop is behind this green plane. Because in general, this three-dimensional view is hard to sketch, especially on a piece of paper. How about the vector equations for a magnetic force on a general current carrying wire? Now, when I say a general current carrying wire, imagine the fact that a current carrying wire might not necessarily be straight. So, if the wire is curved, then the magnetic force is going to be due to a small element of wire. Okay? So imagine this is our little small element of wire, ds. Imagine the current is running this way along the wire, okay? And imagine that we have a certain magnetic field like so, okay? So what we're going to have is dFB is equal to IDS cross B. That is to say, if the wire is in some path, and call that path S, notice that a little bit of force on the wire, some differential amount of force, is due on that differential arc length, ds. I is the electric current, and then again, B is the magnetic field vector. Therefore, if you want the total force on a section of current carrying wire, not some infinitesimal piece, but some finite piece, you need to integrate this from some initial to final, some A to B, S arc length position. So the idea is that S equals A, S equals B. Now, by the way, in general, S equals A and S equals B does not give us a whole lot of information between these points A and B. In general, you might need to look at these as some sort of position vectors from the origin. Maybe you need to establish some geometry or some axis, but in general, this is an arc length, and somehow we have to deal with this geometry. Assume the electric current is constant, and then again, the direction of the magnetic force vector is given by the direction of the ds cross B. Okay? and you have to add all those up, because that's what a line integral means. So remember, a line integral means you integrate along this curved section of wire. Okay? So it's a line integral. You can imagine each of these little ds vectors are tangent to the wire at infinitesimally small points, and you add up all those little tangent vectors. So that's the idea. This example I will perform in a later video, as will I perform this example. Now the first example is for a straight piece of wire, okay, like so, and with a uniform magnetic field. The second example has a uniform magnetic field, but it doesn't have a straight piece of wire. Here we have a semicircular piece of wire. Okay? So we'll have to perform those in a later video. Okay, I want to talk about the torque on a current loop and the concepts. This is actually really important to the concept of electric motors. A current loop on a rotating shaft in a uniform magnetic field is the heart of an electric motor. So let's imagine we have a uniform magnetic field that points from left to right in this diagram. And let's suppose we have electric current running in this direction, which is counterclockwise in the same plane that we see depicted on the screen. Notice that the electric current that's going anti-parallel, that's segment 1, or parallel to the magnetic field, will have zero magnetic force on that. And we've discussed this before, because that's either the sine of 180 degrees or the sine of 0 degrees, which we know each of those to be 0. So there's no cross product and no magnetic force. However, segments 2 and 4 will each have magnetic forces on them. Let's think about what those magnetic forces should be. So we have to perform the right-hand rule. So we're going to point our fingers in the direction of the electric current. We're going to rotate them in the direction of the magnetic field. And the thumb is going to point in the direction of the magnetic force. So for this portion of wire, it's going to be out of the page. So out of the page. And then for segment 4, the electric current this time is up, and the magnetic force is still to the right in the diagram. So the thumb this time points into the page. So if this one is out of the page, and then this one is into the page, the entire current loop is going to rotate like so. In other words, it's going to rotate such that side 2 is going to move towards you out of the screen, and side 4 is going to move away from you. So in fact, if you looked at the loop from above, it would rotate counterclockwise. If there was some axis between these numbers 1 and 3, it would rotate counterclockwise as viewed from above. In fact, it's actually going to rotate to align itself with this magnetic field external. I'll say more about that in a moment. So again, only segments 2 and 4 are perpendicular to the magnetic field to have a magnetic force. So if we view in the plane here, let's imagine you take some plane right here through 2 and 4. So take this loop and sort of look at it on its edge. You'll see that there's a magnetic force upward, that's again out of the page, and there's a magnetic force downward, again that's sort of into the page. And this thing is going to rotate, again, counterclockwise when viewed from above, or clockwise when viewed from below. So, notice that the length of these segments are B along this direction and A along this direction. So, notice that from here to here, that's B over 2. Imagine that this is the axis, straight through 1 and 3. Okay, so with that in mind, with this F2 and F4, if you view the current loop canted at an angle theta to the magnetic field B, notice that we're going to have to consider the torques here, because they weren't just maximum torques before. This B over 2 sine theta, and there's another one over here, that's basically the lever arm. Now remember from physics 1 what the lever arm is. This is the portion of the radius that is perpendicular to the force. And as a result, that's the part of the radius that really counts. So you should multiply lever arm times this force to get the torque. Okay? So the magnitude of the torque on the current loop in terms of the physical quantities is given by this. Torque is equal to IAB sine theta. Now this theta is the angle between the area vector. Now the area vector is perpendicular to this loop. Theta is the angle between that area vector and the magnetic field vector. I is the magnitude of the electric current. And capital A is the magnitude of the area of that loop. So when you multiply all this out, you get a torque, and that's going to be in Newton meters for SI units. Okay? Remember, that's SI units. English units would be something like foot pounds, but again, we work in SI units in this class, and that's how I teach through these things. So define this area vector for these loops, and it has magnitude of A, has magnitude of the area itself, which is units of meters squared. And it's always normal, which is to say perpendicular to the current loop, pointing in the positive direction according to right-hand rule 2. That is shown in the lower right figure. So notice this area vector for this particular loop is pointing upward in this diagram. And why is that? Well, as viewed from above, the electric current is running in a counterclockwise direction. If it's running in a counterclockwise direction, we're going to use right-hand rule 2, which says, take the current loop, rotate your right-hand fingers in the direction that the electric current already runs, and your thumb points in the direction of the area vector. Okay? Therefore, the torque vector as a vector cross product can be expressed as this. So, mu vector cross B vector. Now, by the way, this mu vector is sometimes called the magnetic dipole moment. I'll get to that in a second. This is not coefficient of friction. Furthermore, that's going to be the direction of the area vector of the loop. So from the previous page, remember we had IAB sine theta. Well, now we have IA vector cross B vector, area vector cross magnetic field vector. Okay? And now we actually get a torque vector, and this vector also shows the axis direction. So this is the magnetic dipole moment. Its mu vector is I times A vector. That's going to have units of amperes times meters. Notice the magnetic dipole moment is basically the direction of the North Pole axis. If this electric current in this loop produces its own magnetism, which it will, the North Pole will be in the direction of the area vector. So the magnetic dipole moment will always be in the direction of the area vector. Okay. So this magnetic dipole moment is the direction and strength of the magnetic field created by a rotating current. It tends to align itself with an external magnetic field. Now, if you remember that loop from the previous slide, was turning itself to align itself with that external magnetic field. And it turns out that the North Pole of this loop wanted to line up with the direction of the magnetic field lines and the direction pointing towards the North Pole of that external magnetic field. Now, if there are n coils instead of just a single loop, you just take the magnetic dipole moment and multiply by capital N. And N is like an integer, so it's just n times larger. And I mentioned the units are amperes times meters squared. So here's how to pictorially think about this magnetic dipole moment. If the current is running counterclockwise as viewed from above, if the angle is 90 degrees, that's the maximum torque that this loop will experience. And the magnetic dipole moment, again, is going to point upward if the current is running counterclockwise, because we curl our fingers in the direction of the electric current and the magnetic dipole moment moves upward. But again, the magnetic dipole moment should rotate itself to align itself with the direction of the external magnetic field. So over time, the dipole continues to rotate, that is the dipole moment, and it will continue to rotate as theta decreases and the torque decreases, but we still have torque in the clockwise direction as viewed in the screen. And notice when the magnetic dipole moment aligns with the external magnetic field, theta equals 0, sine of 0 degrees is 0, so there should be no torque, and the loop should stay in that orientation. Now, by the way, suppose you have two loops here. Suppose one has current running, let's see, that looks like clockwise as viewed from above. You would say the magnetic dipole moment then points downward. And that's based on right-hand rule 2. And you can see that since your thumb points downward, look at this. The magnetic field lines all point downward. But notice that the magnetic field lines will move through this loop, almost like this loop were its own bar magnet, where the kind of the north end of the magnetic field lines come out in both directions and form these closed loops. Notice that this magnetic field line is moving upward locally, and the tangent vector to that magnetic field line is the magnetic field vector at that point. Well, if there's another current loop which has the current running counterclockwise as viewed from the right, so if this is the direction of the current, notice that's going to have, by right-hand rule 2, a magnetic dipole moment pointing to the right. So that's going to realign itself to be upward so that its magnetic dipole moment will align itself with this external magnetic field. So the field due to loop 1 points upward. It exerts a torque on the magnetic dipole moment of loop 2, and loop 2 will rotate counterclockwise until its magnetic dipole moment lines up with that field. Now, here's an example of an electric motor. Notice that an electric motor has a force upward, a force downward, but it's at a radius to this shaft, and it's producing a torque. Notice there's a strong magnet here with the magnetic field lines running from north to south. Okay? And then notice that here we have a voltage source, an electric current running into here, but also a commutator, which reverses the current direction in the loop every half cycle, so that the force on the one side, say the left side over here, is always upward, and the force on the other side here is always downward. Because otherwise you could imagine the torque would cause these loops to turn over and then overshoot, and then it would turn back over and then turn back over, so it would just keep flopping around. Instead, with a motor, we want the rotation to go the same direction, so we cleverly use this commutator and these brushes to change the direction of the current every half turn. And hence, that's essentially very much like an alternating electric current direction that this armature of wires receives. So here's just another example where there's electric current coming out of the page, electric current going into the page, and nothing shown right here. Okay, there's zero torque because the current is such that the angle between the current and the magnetic field is 0. But what if we have a situation where there's maximum torque? Well, that's going to be because if you put this current and you turn this loop somewhat, notice that the electric current that's here, that's out of the page, you want to do I cross B, the force is up. Here it's into the page, so that's I cross B, it's down. So this loop should turn over. In other words, it should turn with a torque that's clockwise here. Notice that we can also have negative torques. Negative torques are going to turn us the opposite direction of what we see here. Okay? So if this torque is turning clockwise, this torque is turning counterclockwise. So the loop on its own will just tend to oscillate back and forth in a uniform magnetic field, which in practice is generally not best. With an electric motor, we want the loop to continue rotating in the same direction. So to get continuous rotation, the use of brushes or a commutator will switch the direction of the current every half rotation. And again, I mentioned this. This is receiving alternating current. Now the source here is a battery, which is a DC source. But look at these brushes right here. Look at this commutator. Notice that every half turn we switch the direction of the electric current. Okay, so they are the brushes right there. These brushes are in contact with this commutator every half turn. So by the way, what is actually happening is the input is electrical energy and the output is mechanical energy. That is to say, the potential energy source is the battery. The mechanical energy output is the motor itself. This is an example of a loop with a certain radius and a certain current, and I will perform this calculation in a later video. Now, how about induced magnetic fields of currents? We've seen that magnetic fields exert forces on currents and moving charges. Since a current is a moving charge, it produces its own B field, its own magnetic field. Now, before we saw that loops of wire, and by the way, if you have many loops of wire, that'll be a solenoid. I'll talk about that later. Carrying currents produce magnetic, that's B fields, pointed in the direction of mu vector. That's the magnetic dipole moment. Okay? Now, for example, a current loop in a rotating shaft has an equilibrium orientation, like any compass needle. So, in that situation we see pictured down here, the loop will rotate. But in this situation, the loop is in equilibrium. It will not rotate. So the loop will rotate until the induced magnetic field of the loop, that is the magnetic dipole moment, mu vector, aligns with the applied magnetic field. So, suppose you want to know the magnetic field generated by either a single moving charge or a current carrying wire, and that single moving charge or that current carrying wire is in some general orientation. And suppose you're interested in what is the magnetic field at this point P, or maybe this point P prime. Now notice ds is the differential tangent vector to the direction of the to the direction of the electric current. Theta is the direction to r vector. Now r vector is a radius unit vector as long as it has a hat. So remember that hat means unit, which means length 1. So this gives you the vector direction from ds to the point P. And notice here's an additional r hat. R hat is local to whichever point you're talking about. Now the distance from the ds point to P, or to this P prime, is going to be some r distance. And again, let this wire carry current I. So to figure out the vector magnetic field from a general moving charge or path of current distribution, we must use the Biot-Savart law. Now, by the way, let me just warn you, the Biot-Savart law is not for the faint of heart. It's quite a difficult vector and calculus type equation. Kind of looks like this. This is quite difficult to grasp. Notice that this is the Biot-Savart law for a single moving charge. A charge q moving at velocity vector v, and that velocity vector v, let's assume it's constant direction, but in general this could be a dv, and this would be db. So it's cross r hat times mu naught over 4 pi, and then r squared downstairs. Notice also, if we were to do the Biot-Savart law with electric current, it's going to be dB is mu naught over 4 pi times I, the electric current, ds vector cross r hat, okay, over r squared being the distance between them. Okay, couple things to say. First off, these are quite difficult cross-product vector equations. That's the first thing. Second thing is, r hat has magnitude of 1. So identify the direction to the point of interest. V vector is the vector direction of the moving charge. ds vector is the small differential element of wire that's moving in a certain direction. And look at this 1 over r squared dependence. That is to say, magnetic field follows the inverse square law. Just like the gravitational force does, which is a field, just like the electric force does, which is also a field, the magnetic force does. Now, by the way, this mu naught we have not examined yet. That is going to be the so-called permeability of free space. Now, the permeability of free space was defined given how Teslas were defined and various other things when magnetism was being discovered. So this is its exact value. Its exact value is 4 pi times 10 to the minus 7th Tesla meters per ampere. Okay? And it's basically defined based upon certain units and SI units and so on. Now, the direction of the magnetic field, dB vector, or for that matter, B vector, is perpendicular to the r hat vector and the ds vector. Or you could say over here, it's perpendicular to the velocity vector of the charge and the r hat vector. Okay? So that's why at point P here, it's out of the page. At point P prime here, it's into the page. How can we verify that? Well, the one that's out of the page, notice the ds is this way, the r hat vector is that way, so the thumb points out of the page. This other one, P prime, the ds is that way, the r hat is that way, the P prime is into the page. Remember, these magnetic fields must be perpendicular to the plane that contains both ds and r hat. So if ds and r hat are in the plane of this screen that you're watching this video on, then the magnetic field vectors here must be perpendicular to this screen, either out of the page or into the page. So again, like I said, magnetic field magnitude follows the inverse square law, and the Biot-Savart law in general must be integrated over all the elements in a wire to find the total induced vector magnetic field coming from the current carrying wire. So here's a sort of a three-dimensional, better pictorial depiction of the magnetic field direction of a segment of electric current due to that electric current flowing and using the Biot-Savart law. Imagine there's an electric current, and this X here means into the page, like so, and then here it's still going into the page. You can see it three-dimensionally. Here's the little delta S, which again, in calculus sense, you can shrink that down to ds. R hat vector, again, has length 1, and it points up to this point of interest. That's the point P. So, I is in this direction, R vector is in that direction, the thumb points this way, which is the direction of the magnetic field. Notice the magnetic field of the short segment of current is in the direction that's perpendicular to S and S vector and R hat. Notice that it has to be perpendicular to this plane. Notice this plane right here, B is perpendicular to it. So you have to really think about this three-dimensionally. And the Biot-Savart law tells us that the magnetic field is in the same direction as the cross product of the electric current and the position direction, but is displaced up to the point P. How about if a wire is straight? Well, if a wire is straight, it should produce its own magnetic field. So, here we have to find that direction using right-hand rule 3. Now, don't get confused. These right-hand rules, everybody give them a slightly different number. I've chosen to give them the numbers that I've mentioned. Okay? So right-hand rule 3 says the following. If you have a straight piece of wire, point your thumb in the direction of the electric current, and your fingers rotate in the direction that the magnetic field circulates around that wire. Okay? So it has to be sort of like so. Around this wire in concentric circles. So notice that these concentric circles are surrounding this piece of wire three-dimensionally, and that's because that's the direction that the magnetic field circulates around this wire. The magnetic field magnitude for this particular scenario as a function of radius for a long straight current carrying wire is equal to mu naught I over 2 pi r. Now, by the way, you can derive this above equation using the Biot-Savart law, but very soon in the next set of lecture slides we will use Ampere's law, and it's much easier to derive this relationship for a long straight current carrying wire. So notice that the magnetic field of a wire depends upon this constant mu naught and 2 pi, 1 over 2 pi, so that's a constant. But the larger the current, the greater the magnetic field. And the larger the distance you are away from the wire, the smaller the magnetic field. And it goes as 1 over r, dependence. So it's inversely proportional to the radius distance away from the wire is the magnetic field magnitude. So here's a couple geometries you should be aware of in terms of magnetic fields. What about a circular loop? Notice that the magnetic field seems to go straight through and seems to circulate around the edges here. Okay? So it creates a field that looks a lot like a bar magnet. And the direction of the field through the loop's center can be found using the right-hand rule. Okay? So let's make an analogy. If you have a bar magnet, the magnetic field lines go from south to north and then out of north back into south. So the bar magnet's field is a dipole field. The field lines go into the south pole, come out the north pole. Now in the same way, if this wire here is having current going around like so, where if you view it from the right-hand side, it looks like it's going counterclockwise. Notice that you should use right-hand rule 2. You should take your fingers and wrap them in the direction that the electric current is moving, and the thumb points in the direction of the north pole of this magnet. Remember, the north pole of this magnet is also the direction of the magnetic dipole moment. So this current loop has a dipole field as well. As with a magnet, we assign north and south poles based upon where the field lines enter and exit. Now, I'm not going to go through the derivation, but at the very center of this loop, the magnetic field at the center is mu naught I over 2r. Notice I didn't say mu naught I over 2 pi r. I said mu naught I over 2r. So that's the correct equation for the magnetic field magnitude at the center of the loop. By the way, if you're not at the center of the loop, in general, it's very complicated to calculate. So I'm not going to discuss that in part of this lecture. Okay? Now, what if you're not just at the center of the loop? What if you're above the center of the loop, off axis here or here? Okay? So we'll take a look at this in a later video, but you can actually calculate what the magnetic field is along the central axis of the loop. Okay? So I'll show that later as well. Here's a couple examples to think about, okay, in terms of the geometry. Notice that here's pictorial representations of magnetic fields of current carrying wires. Notice if this electric current is, let's say, moving down, you point your thumb in the direction that the electric current is moving, and notice your fingers wrap in the direction of the way the magnetic field circulates. Notice here the magnetic field is circulating clockwise as viewed from above. Okay? Remember, anytime you see an X, that means the electric current goes into the page, so you should point your thumb in this direction. Okay? So suppose we have an example where the electric current goes into the page, then the magnetic field should be clockwise in the plane of the paper. That's because our fingers curl clockwise, so the magnetic field lines are clockwise and circulating around this wire. Notice the magnetic fields are longer where the field is stronger, and the magnetic field lines are closer to this wire where the magnetic field is also stronger. Okay? The magnetic field vectors are always tangent to these magnetic field lines. Now, what if we have current in a loop? Notice that we can either look at the loop in the plane of the loop or on edge. If we look at the current in the loop in the plane of the loop, notice that suppose the current is going round counterclockwise as viewed in the plane of this screen. Well, you can point your thumb in the direction that the electric current is moving, and notice your fingers, that is, your fingers would wrap around like so with your right hand, and notice when the fingers are wrapping such that your fingers are pointing through the center of the loop, everywhere inside this loop, the magnetic field is coming in a direction out towards you. So out of the plane of the screen. But notice that if your thumb is pointing this way and your fingers are pointing into the screen, notice all these X's out here. Everywhere outside the loop, the magnetic field is pointing into the screen. So you can use the right-hand rule if the loop is in the plane or on edge, because you can point your thumb in the direction the current is moving and you can see which way the magnetic field lines circulate around. Again, this is always given by this so-called right-hand rule. But now we're using right-hand rule 3, where the thumb is the current and the fingers are the direction of the magnetic field lines. So if you use the right-hand rule for fields, you find the direction of the field lines. Near the wire, the field lines are almost circular. The field will emerge from the center of the loop and return in the opposite direction outside the loop. The last slide for this lecture says the following, and a brief historical note as well, that it was in 1819 that Hans Christian Oersted, discovered that an electric current in a wire causes a compass to turn. Notice that here's a wire with all these compasses are pointing towards north. That is their red side, and the white side is pointing towards south. Okay? If you turn on the electric current and the current is running upward, the thumb points upward, the magnetic field lines should circulate counterclockwise as viewed from above, and the compass needles look like they rotate counterclockwise. Because of that strong current, they experience a strong local magnetic field nearby. So the compass needles are always tangent to the circle with the North Pole in the direction that your fingers are pointing. So notice that this is exactly what we see with these iron filings if they're near a long straight current carrying wire in an actual experiment. Ladies and gentlemen, thank you very much for watching this lecture on electric currents and how they relate to the creation of magnetic fields and how magnetic fields affect electric currents. If you like this content, please smash that like button and subscribe to the channel to grow the channel. Please share this amongst your social network. Also, I want to thank you for watching this video, and I look forward to seeing you in the next video.